Stanford University.
Hi, my name is Biswapesh, and I am from Google. And today we are going to talk about the YouTube data warehouse. As Jacob said, I think previously I was thinking of doing a presentation on Dremel and Tenzing, but then I realized that we have kind of talked to death about it. And what I really wanted to do today is something that probably we haven't done before. So previously we had talked about various Google technologies. I think we have seen papers on MapReduce, we have seen papers on GFS, on Tenzing, Dremel, Sawzall, and so on and so forth. But we have essentially looked at these technologies in isolation. Bigtable, another important one. But we essentially had looked at these technologies in isolation, and what I'm trying to do today is present a case study in terms of how all these technologies are brought together to create a working system. And the case study I'm going to present is the YouTube data warehouse, which is one of the several data warehouses at Google. So just to give you a quick overview, one of the things that we are very keen at Google is we are kind of a bit obsessed about building on top of our own stuff. So, and there are good reasons why we want to do that. Predominantly, they are economic reasons. So we have a lot of very cheap computers, and we believe that it's a lot cheaper to build on our stack because we have a lot of data. Our data typically always runs in petabytes, and trillions of rows is very expensive to go for third-party products. And since we have very cheap hardware, a lot of which sits idle some of the time, it's usually a good idea to build on top of that. So in terms of YouTube data warehouse history, we originally started when YouTube was kind of not yet part of Google. YouTube was building its warehousey kind of database on top of Oracle, and somewhere during the acquisition period, they transitioned to Oracle, from Oracle to sharded MySQL, and they wanted to do it cheaper because we were scaling. The number of videos and number of watches was kind of exploding, and we wanted to scale better without increasing cost too much. And we were then on the MicroStrategy platform in terms of our reporting. So currently, our platform is 100% Google stack. So we use our native column IO and GFS for storing the data. We use a combination of Sawzall, Tenzing, Python for doing analytics and processing the data, ETL and stuff like that. And we use our own reporting and dashboarding solution, which is called ABI, which I believe we haven't talked about previously. So in terms of stats, briefly, I think we all know the data flow. The YouTube website gets a lot of hits, a lot of watches, channel views, user signups and stuff like that. It all gets collected into the YouTube logs clusters, which then get processed by a variety of tools. A lot of people do direct analysis on those logs. There are a lot of ETL pipelines that pull from those logs and then process data into GFS in a more compact form, typically in a nested relational structure, which is columnar in nature. And then we have a bunch of tools on top of that to kind of further process the data and also to create dashboards and so on. So by the way, one thing, I know that we are not taking too many questions, but my slides are actually designed to be a little more interactive. So I'm okay with being interrupted, just FYI, if you don't mind. Yeah. Okay. So this is the only diagram, I promise. This is a pretty basic stuff. I think what's interesting is not so much the data flow itself, which is very, very standard in most data warehouses, but more of what kind of internal tools are being used at which point in the pipeline. So briefly speaking, most of our data in terms of volume comes from the logs, as I believe is the case with most other internet organizations. A fairly significant chunk of the so-called dimension data, which is things like users and metadata about videos and stuff like that, comes from MySQL sources, which drives the YouTube front end. A lot of the data also comes from Big tables. Big table is typically used for secondary process data, which is also used for serving some of the data for online purposes. For example, I believe some of our featured video stuff and things like that are driven off big tables. But big table is also used as a backend for various other types of data forecasting and summarized analytics and things like that. And we have a real-time pipeline. I think Facebook and eBay people have talked about that, and LinkedIn people, which kind of populates these big tables in real time. But I'm not going to go into the details of that. So in terms of the pure warehousing part of the effort, we have our ETL is mostly based on Sawzall Tenzing with a glue of Python and C++ MapReduces. We're going to talk a little bit more in detail about exactly when we use what. And the warehouse itself, in terms of data, is purely column.io on GFS and sort of the newer version of DFS that is being currently developed. In terms of how do we get data out of the warehouse, there are three use cases. First is, can I click on that? Does that work? There you go. So the top right one, this is our standard real-time dashboarding reporting thing. And this is based on a three-tier, pretty standard one. We have the ABI, which consists of a front end, which is based on Google visualizations, internally called as GVis. I guess some of you are aware of that. Built on a Java layer. And there is a middle tier, which talks to the Dremel service. Again, I'm assuming most people are aware of Dremel. This is our ultra-fast real-time querying engine on columnar data. And the backend data is obviously the YouTube data warehouse. What's interesting is that the same Dremel service also hooks directly against other logs, which is, I should have shown in the diagram, which I kind of missed. So an analyst can actually query the warehouse, which is process data in real time using Dremel, and he can also go back, not for the entirety of logs, but the last few days of logs, directly to the logs to do more in-depth analysis. And because the logs are nested relational in nature, and Dremel has very good support for nested relational data, it's quite easy to query the logs using Dremel's kind of extensions to the SQL language to make real-time decisions in terms of, for example, if I take the example given by, sorry, for eBay, Tom from eBay, like homepage analysis. So you can do something like, what is the path from the home page to the watch to the favorite to the comment and things like that. You can do that using Dremel directly on the logs by using a Dremel user-defined function or some of the nested relational functions that are available in Dremel. So the other path which is taken by some is using the Tenzing service. And this part is interesting because one of the main differences, I think we'll talk about it a little later, is that Tenzing is based on top of MapReduce and scales better in terms of doing large joins, and in general has a better support, at least at this point, in terms of SQL operators. So we can do very large joins and very large set operators and very large intermediate tables and pipelines and stuff, which is useful in many situations when you want to go into more in-depth analytics. So the next few slides, I'm going to talk about the various pieces of the architecture and what are the pros and cons of each and where we use each of these.
When you say Tenzing scales better than what?
Better than Dremel. Yes. So I think in terms of scalability, I would encourage people to look at the paper we recently published in terms of MapReduce beta sort, which is basically the underlying technology of Tenzing. So we published some numbers there, and I think they were something like 30 minutes to sort a petabyte of data on 8,000 machines or something like that. So we do scale fairly well. Not infinitely, but close to that. So Sawzall, I think, I'm assuming many of you are familiar. This is our scripting language built on top of the MapReduce framework. So Sawzall is interesting in the sense that it is both a language and a framework. So there's a little bit of difference between Sawzall, the language, and what we call the Sawmill, which is basically, or the MR-Saw, which is kind of Sawzall language bolted on top of the MapReduce framework. So the Sawzall language itself has been open sourced. And I believe it should not be very difficult to port it onto Hive, though it's kind of a little bit of a C++ mess over there. But so Sawzall is essentially a awk-like language. I think that is the closest thing that comes to mind. It's a simple procedural language with a lot of support for text manipulation and stuff like that, which is very useful for logs processing. What makes it very interesting from a Google perspective is that it is used extensively, at least before Dremel and Tenzing came in. It was pretty much the exclusive tool used by the analysts and lots of engineers to do processing on top of logs. And predominantly, it was because of the very fast development cycle. It was essentially like you write an awk script and it runs on the entire like 10 petabytes worth of logs or whatever. The big thing that the MR saw built on top of Sawzall, the language, was essentially the support for MapReduce-based aggregators. So you could, in the map phase, write a fairly complex Sawzall script that applies a fair amount of business logic. And in the reduce phase, you can define your aggregators, or you can use many of the inbuilt aggregators like count distinct and sums and max and mins and like medians and statistical functions and so on and so forth. And you could then run this on the cluster, and it would act like a hugely distributed kind of complex aggregation engine, which made it really powerful, because you're like using a few lines of code without compilation, you could do very complex analysis on fairly massive volumes of data. So another thing that we have in our inbuilt Sawzall MapReduce implementation is security support. As you know, logs is pretty sensitive, and Sawzall runs directly on logs, so it is very essential to build a lot of security measures underlying the Sawzall IO infrastructure to make sure that people are not accessing fields that they're not supposed to, and so on and so forth. Sawzall is a procedural language. It is like both a pro and a con. It's a fairly powerful programming language in its own right. So you can have all those loops and complex functions and user-defined functions and so on and so forth. You can even pass functions to functions and I don't know, crazy stuff. But the con side of that obviously is that it's not quite as easy as writing SQL. Also, Sawzall has a fairly high overhead in terms of startup and shutdown, as you can imagine, because it's essentially spawning a MapReduce. Every time you run a Sawzall job, it spawns a MapReduce. So how do we use Sawzall in our warehouse? Predominantly ETL of the YouTube logs. So whenever we want to pull from the logs, Sawzall is the language of choice, because fast to develop, easy to test, no compilation phase requires, and it's quite fast. Sawzall internally compiles to native code. We have a direct compilation phase to compile it to the underlying architecture, and it runs. So it is, though not quite as fast as C++, but it comes fairly close in a lot of standard situations. A lot of Sawzall is also extensible by writing C++ extensions. We call them intrinsics, basically functions, which makes it quite powerful. So ETL of YouTube logs, complex one of logs analysis. So if you want to do an analysis, so predominantly the way a typical data set comes into the warehouse is some analyst starts with a fairly complex analysis. Let me do this really complex stuff and find out some interesting trend, and then maybe use R or some of those statistical languages to see whether the trend is, whether we can get any sense, make any sense out of that data set. And if yes, then the decision point comes regarding, do we want to track this data over time? If the answer is yes, then typically somebody would go and build an ETL on top of that and bring that into the warehouse, and then we'll schedule it using our scheduler architecture and things on, which I'll talk about a little later. Okay, the Tenzing, again, I'm assuming people are reasonably familiar. This is something that we presented at VLDB earlier this year, something we've been working on for a while, about a couple of years. So it's basically think Hive, like SQL on MapReduce with some interesting twists. The main twist, I think, main twists are, obviously it's built on top of Google MapReduce framework. It's a very efficient native C++ implementation. It has a very, very strong SQL support, so pretty much all kinds of weird joins and analytic functions and setups. We have tried to implement as much of SQL 92 as possible. And it is completely heterogeneous, so you can read and write various systems, various sources. You can read from sharded MySQL right to column IO. You can read from column IO right to Bigtable and so on and so forth. You can join a Bigtable data source with a column IO data source with a single SQL. So that makes it quite powerful, especially for analytics and ETL. Couple of limitations. Complex procedural code, again, we use Sawzall when that is really required, for example, in really complex logs processing. Higher latency than Dremel, this is MapReduce. It has some latency. We have done quite a bit of work to bring down the latency. So it is now in the order of maybe 5-10 seconds, but it is still significantly higher than Dremel, which has like millisecond latency. And support for nested repeater structures are weak. Again, one of the core strengths and weaknesses of Tenzing is that it is predominantly a SQL engine. So it requires some kind of a like relational data model. It doesn't really support nested relational quite as well as Dremel. It has some limited support for it, but Dremel has far more flexible support. Coming to usage, again, ETL for non-logs data. One of the things that prevents Tenzing from running on logs, two things. One is that support for nested relation is kind of limited. Second is it doesn't quite have as much of the security infrastructure that Sawzall Sawmill has to run directly off the logs. And so it's used for ETL of a lot of the non-logs data, for example, pulling from the big tables, pulling from the various MySQL instances, and also for reasonably complex analysis where you want to do like a pipeline of which is possible to do using SQL pipelines. And Tenzing is extensible, as is Dremel, using a variety of user-defined functions. Tenzing actually uses Sawzall as the extension language of choice, whereas Dremel uses Lua. Am I going too fast? I mean, feel free to interrupt. Okay. Right. So we come to Dremel. This is our third analytical engine. And again, there is a paper which was published, I believe, last year or the year before last. I forget. So current use in YouTube warehouse, predominantly this is the only backend that we use for our real-time analytics. So it sits behind API and it answers all the API queries in SQL regarding aggregations, filters, and stuff like that. Interactive log analysis, as I said, like Dremel, then one good thing about Dremel is that it runs on the processed data as well as directly on the logs. So it is quite easy to use Dremel to cross-check data in real time and things like that. Key strengths, very low latency. Dremel is very, very fast, very low latency, like typical latency of a small query is under a second, typically in like a few milliseconds. SQL support is good, not as great as Tenzing, but it's reasonably good. It has a very strong nested relational support, so you can query structured data very, very well with Dremel, and we have extensions to SQL to cover this. Again, the Dremel paper goes into more details. And finally, Dremel has limited access to logs, not as much as Sawmill, but Dremel has access to the last few days of logs, which are in columnar format. Limitations, again, compared to Tenzing, it has less support for the higher level SQL constructs. It doesn't support the bigger joins. It has limited support for set operations. It has limited support for analytic functions like ranking and stuff like that. It is extensible using the Lua programming language, so you can write Lua to write reasonably complex table level and like scalar functions. The inherent library in Dremel is somewhat limited compared to Sawzall and C++. Like it's not very hard to extend, but you need to write C++ extensions to create new functions in Dremel. And as things stand now, Dremel is more of a Mustang tree kind of, serving tree kind of infrastructure, so it doesn't scale quite as well as MR in terms of when you're talking about relatively large volumes of intermediate data. So here is a rough comparison of where we at with the three different backend technologies that we talked about. Sawzall, higher latency, very high scalability, no SQL support, but very, very highly powered. It has lots of inbuilt functions and stuff like that, which handles Google specific things. Tenzing, again, medium latency, high scalability. It's built on the same framework as Sawzall, so the scalability is the same. Very good SQL support, power, medium, whatever is provided by SQL plus programming extensions. Dremel, very, very low latency in a few milliseconds. Medium scalability, it scales very well in terms of pure scanning. When in terms of more complex operations, the scalability is somewhat limited compared to MapReduce. SQL support is again good, but not perfect. And in terms of power, it is probably limited mainly because of the limited SQL support. So what's going on in this part of the world? We are trying to merge. There is an effort currently underway which is trying to merge some of the best parts of Tenzing and Dremel together, which predominantly consists of adding some of the MapReduce capabilities to the underlying Dremel engine so that we can get the best of both worlds in terms of very, very low latency and high scanning speed of Dremel combined with the power of doing really large shuffles so that we can do really massive joins and other complex SQL in the order of a few milliseconds and hopefully in a few seconds. Materializing large result sets. And another thing that Dremel currently lacks is Dremel is kind of built for columnar access. So it has certain inherent limitations in terms of accessing other types of data. So there's a fairly largish effort going on right now to enhance Dremel's capabilities in terms of handling different other sources and targets. More powerful analytics. So we are trying to see how far we can take SQL in terms of extending SQL through more powerful analytical functions, in terms of writing table-valued functions in Sawzall, Lua, and different languages to kind of go beyond SQL essentially. And hopefully, our long-term plan is to kind of merge these two backends into a single backend, which will have a lot of the MR-like characteristics and also support a vastly superior set of SQL compared to like some of the commercial offerings or our current offerings. And again, I guess this is, most of you guys already know, Dremel is available externally right now as the BigQuery platform where you can put data into BigQuery, you can import your data into the BigQuery service and then query your data very fast, and the underlying infrastructure supporting that is Dremel. We are going to bring a lot of these improvements into the BigQuery platform down the line. Okay, and finally, on the reporting front end, this is nothing like, so this is basically our in-house inbuilt reporting and dashboarding solution. The name is ABI, Actionable Business Intelligence. This is a platform that we built from the ground up to replace a lot of the proprietary platforms that we were building our solutions on like MicroStrategy. We were also using, I believe, Oracle reports and things like that. So again, the main advantage of this platform is it is very, very tightly integrated with the rest of the stack. So it can use Dremel as the backend using the Column.io data source, which gives it a very high degree of scalability, and it scales very cheaply. It runs on our data centers on top of the Google data center infrastructure. It uses Google visualizations, which is again project that is already out there. It's called GViz, which provides a lot of very nice visualizations, graphs, charts, and pretty pictures and stuff like that. We have done some extensions on Flash-based extensions for some of the really funky stuff. And current use is data warehouses predominantly. Most of our reports and dashboards are based off this. Okay, this bit is about a lot of the messy details that kind of go into a typical warehouse. A lot of our glue code is Python. This is predominantly code that like has wrapper around the Tenzing code and this Dremel sequels and things like that. Doing small scale extracts from CSV files and reference data and blah, blah. Scheduler, we actually built our own in-house scheduling framework. This is predominantly used by engineers to configure the way the job runs. It has again, the scheduler knits very tightly into the overall infrastructure. It understands about GFS, it understands about Column.io, it understands about reading headers. It understands about how GFS data is replicated across different data centers. It understands about topology, and it understands about when logs processing is done and things like that. So you can build custom triggers around, hey, as soon as this day's log is finished, you should kick off this job, and then there are downstream and upstream dependencies. It has a standard scheduler stuff in terms of time-based dependencies like action-based dependencies, file presence-based dependencies, and so on. One final thing that I should touch about, before that, C++ MapReduce is still in vogue in a limited way. A lot of the very, very custom pipelines have to use C++ MapReduce. One good example is when a certain library is not available in Sawzall. For example, let's say an RDF library to parse, or XPath library is something that is not available in Sawzall, then you have to resort to C++ MapReduce or write a intrinsing in Sawzall and then parse that. So a couple of our pipelines are still based on C++ MapReduce, but predominantly we are on to Sawzall and Tenzing. And finally, query rewriter. This is something new that we are working on. This is still kind of a little bit of a work in progress. It has gone into production and we are seeing good results, but it is not quite like at the end of the development yet. It's still under active development. So this is a layer that sits between the reporting layer and the query engine, in this case ABI and Dremel respectively. And it does a lot of application specific rewrites. So some of the simpler rewrites, for example, materialized view rewrites. So you're targeting table A, that silently rewrites it to target table B because table B is a already aggregated version of table A. Also some more subtle rewrites which depend on understanding application specific logic. So this is the nice thing about like one of the big things about doing an in-house development is that the query rewriter, for example, can reuse the parse tree of the grammar that we have for the Dremel engine. So it basically takes the query, unparses, sort of parses the query into the parse tree, does the rewrites on the fly and reparses it into a Dremel query, unparses it into a Dremel query and just sends it back to the Dremel system. And this has a lot of, apart from the pretty standard stuff in like, for example, avoiding joins by, accessing a denormalized table or creating or accessing the more directly aggregated table instead of the base table, it does some interesting things. For example, if you run a query with a certain date range, it can from the metadata find out specific files that it needs to address, and it can rewrite the data to only access those specific files using Dremel extensions. So it can do a lot of the application specific. So it has a lot of the data knowledge that is built into the rewriter, and we are finding that having a rewriter that has application knowledge is extremely useful in terms of doing very, very intelligent rewrites on the data, which can like get your performance down from like 10 seconds to under a second and even more. Okay, this slide is about performance, and predominantly I think there are 3 different layers: data model, the query engine, and the reporting front end. So just a brief idea about what we do at the different layers to improve the performance of the system. I think denormalized, aggregated, materialized view, this is pretty much standard. We also do a lot of what I think Tom touched upon in the eBay talk in terms of storing the data in a nested relational model, like repeated values instead of using like master detailed tables. That significantly compresses the data, and because both Dremel and Tenzing support this kind of data like nested values and repeated values, that gives us fairly high performance. Range partitioning is pretty standard, I guess. We do a lot of range partitioning, especially on time of the data. We also do a lot of file-specific rewrites on the range partitioning. So for example, we don't, instead of going directly to the metadata layer to find out which ranges to scan, we can pretty much convert the query in the rewriting layer itself to access only particular partitions of the data. So the range partitioning goes on both at the lowest end of the query engine and also at a slightly higher level, which has more application-specific logic. So for example, even though the range partitioning is on, let's say, timestamp, the application logic knows that if the query is on like week ID, which can be from which the timestamp can be directly derived, it will actually do that conversion before sending the query to Dremel. And that means that you can do range partitioning on columns on which the data is not really range partitioned on. Query rewrites layer, I think I talked about this before, using materialized view partitions based on data knowledge and things like that. And the main thing is the rewrite layer is aware of things like hierarchies of data, like date to week to month and so on. It can rewrite queries intelligently to target the right data. Reporting front end, the main optimization there is we are using memcache to aggressively cache the data, especially for the first set of data that comes in. So the first page you see on the dashboard, a lot of the data is pre-cached by memcache, and memcache does a pretty good job of intelligently doing the caching, so that we don't have to worry about it.
Could you give an example of when you can do effective range partitioning, even though the superficial view is impossible to do range partitioning?
Okay, so let us say that the underlying table is, sorry, the question was, can I give an example of a more intelligent form of range partitioning where the superficially doesn't seem to be feasible? Is that correct? Yeah, so I think I touched upon this. So the simplest example is, let us say you have a table which is daily partition. So you have one partition per day, and the metadata of the table knows that this table has daily partitions, which is like one file, let's say one set of files per partition or whatever. So if a query comes that says that give me all the data between for this month of July, right? And it gives a where month equal to July, let's say, and assume that month is a denormalized field in the data. So the application specific rewriter knows that there is a dimensional hierarchy between the month and day. So it can convert that month equal to query into a day equal to query. And it can say that, oh, convert this query into where day between first day of the month and the last day of the month. And then it sends it to the backend. And then the backend just knows that this is a query where I can range partition only, I can only access data for this month. So I guess that's an example. In a typical RDBMS, unless the RDBMS is really smart, the RDBMS will see the month equal to query and assume that I cannot access the range partition by date because the filter is on month, not on date, right? But because the rewriter layer understands the hierarchy between the different data element, it can dynamically convert that on the fly. Does that answer your question? All right, I think that's all I had. My material was deliberately a little short because I was thinking it would be more interactive. But yes?
So you have different types of query engines. You have different types of query engines.
Yeah. So my question was that you have different type of query engines going against the same store, right? It could be Dremel, it could be Tenzing, but trying to access the same data for different queries. So how do you ensure that if suddenly somebody runs big queries on one system, it doesn't affect the latency, performance, stuff like that for queries in other system, and vice versa?
Yeah, that's a good question. So first of all, in GFS, the data is triplicated. So typically, data access is not a bottleneck. So we can have a Tenzing query and a Dremel query both accessing the same data, and the performance impact would be minimal, unless you are like getting 20 queries trying to access the exact same partitions. Lot of the data access is, the more of a limiting factor is basically the computation layers. So if you think about it this way, the data itself is in a set of machines, which is GFS, right? The computation is on a different set of machines. So we have a Tenzing pool of workers, we have a Dremel pool of workers. So there is usually, if somebody runs a Tenzing query and a Dremel query, there is no bottleneck because the underlying data is triplicated, and the computation of Tenzing is happening in a different set of machines from a Dremel machines. There is bottleneck that comes in when it goes beyond a certain threshold. So for example, 10 different Tenzing queries are trying to access the same data. So that is where some things kick in. In both Tenzing and Dremel, we have a per user query limit in terms of how many simultaneous queries you can fire at a particular time. We also have a fairly intelligent cache in the GFS layer. So when the GFS reads the data, it typically caches the data locally in memory and then sends the data across as blocks. So if multiple resources are trying to access the same data, we won't really hit the disk that many times. It will pretty much give the data out directly from RAM. You will still consume the network bandwidth, but it will not really use that much of a disk. So these are the two main methods, I guess.
So as I understand, the Sozo and Tenzing are both based on MapReduce. I think earlier you mentioned Sozo actually has a higher latency than Tenzing. Can you explain why?
Yeah, that's a good question. So the main reason why Sawzall has a higher latency than Tenzing is because in Tenzing we have spent a lot of time optimizing latency by reusing pools. So Sawzall does not use the concept of pools. Theoretically, there is nothing actually stopping. I guess Sawzall from also reusing a lot of the concepts that are there in Tenzing, for example, using worker pools and master pools to reduce latency. But as of now, Sawzall does not use those MapReduce features. Tenzing does. So that is the reason.
So is all the process data in the warehouse stored in the columnar format, column IO format?
Yes.
So, and both Tenzing and the other system, Dremel,
Dremel.
both can access the column.
That's right, yeah.
column data.
So that's the nice thing about segregating your data from the query layer, yeah. So both query engines can access the exact same data. And you can even run Sawzall scripts on that warehouse data. So you can pretty much use any tool, any of the tools on any of the data sets.
So this column IO format, is it the same as what the Dremel paper says?
Yes, yeah, it's the same format. So Tenzing and Dremel like reuse a lot of the underlying infrastructure in terms of like they use, both of them can access column IO. Column IO is, so again the libraries for accessing column IO are kind of abstracted out. So this for both reading and writing. So Sawzall, Tenzing and Dremel, all three of them can use the same libraries. It's just like the Bigtable access library. So the access libraries are in a different layer than the execution code. So for example, Bigtable can be accessed by both Sawzall, Tenzing and Dremel, all of them.
Okay, thanks.
Any other questions for Biswa alone?
What data warehouse design methodologies are you using? Are you guys using, Ralph Kimball or some Inman, or have you, invented your own?
A giant hack. Okay. But no, seriously, I wish there was a good, clean answer to that. But as with most use cases, there is no perfect answer. I guess we follow some of the dimensional like core concepts as so we can say it's kind of Kimball-ish rather than Inmonish, if that makes sense. So the data warehouse is kind of more dimensional, normalized fact, denormalized dimension kind of thing. And it's pretty much followed in most of the warehouses in Google, but again, not all the time. So for example, a lot of our facts are denormalized, semi-denormalized. So it all depends on use cases really. So we don't believe in like sticking to a particular methodology, but we just try to apply,
For more, please visit us at stanford.edu.